Hello boys and girls. We're looking at a super cool car here. This is from the Wikipedia article on simultaneous localization and mapping, aka SLAM. This is what I do in my day-to-day life, and so working in computer vision, I deal a lot with Lie algebras and Lie groups and their use and implementation. These objects are used in mechanics and robotics in particular, and also augmented reality. And this ties to the video that I did 2 weeks ago, where I implemented taking the derivative of polynomials, how that actually works in this kind of discrete sense, where you interpret the derivative as an algebraic operations that is linear and really algebraically defined by, let's say, the derivation rules, product rules, power rules. And this video ties very close to just taking derivatives, and at the same time I give sort of the first baby interpretation and baby introduction to in particular the Weyl algebra, but in the end I will also mention like tensor algebras and universal enveloping algebras for Lie algebras. And so this is very, like, it might sound a little bit off and complicated, but this is going to be very basic, and I think this is going to be good. My motivation really is that in a future video soon, I want to go through this short 22-page paper, I guess, by a guy called Lingle. It reads like he was a student at the time. I googled him. I think he is not working in mathematics anymore, but of course has a STEM-like job. But he apparently wrote this nice summary of some book theorems, and also there are some proofs in this paper. And in particular, he talks about the Poincaré-Birkhoff-Witt theorem, which is a theorem on universal enveloping algebras useful for Lie algebras. And so before I actually go through this paper, I think here on page 18 you can get a glimpse on, it looks a little bit denser than what I had done so far in my videos. But I want to describe that, and for that, to not alienate everybody, I will give a very soft introduction to Weyl algebras today, right? So again, it all relates to taking the derivatives. If you have not seen that video, it will not be necessary that you have seen it. But the motivation is that how to go away from the analysis context where derivatives are defined by some limit process over functions over the reals, for example, and just look at things algebraically and get used to all these rules and the tools as you use them if you deal with Lie algebras. And as I said, this is something I actually do in practical work. So I just point out this related Wikipedia article. So defining tensor algebras and tensor products and universal enveloping algebras. I'm not going to get into too much detail. And recap, of course, in let's say analysis, you can derive product rule for the limit that makes for the derivative. And if you look at monomials, then you can set everything. Like if you look just at, for example, finite polynomials, you can translate everything to very algebraic manipulations. The notion of product rule, if you compare here with that, you can take that as an axiom and define objects which fulfill this kind of relation, and this very much ties then to how Lie brackets operate and so on and so forth. And if you look at monomials, x to the power of r, then you get the power rule, and this is the thing that we are going to consider. So the examples in this video are going to be just one-dimensional coordinate rings, if you will, and as algebras, two-dimensional in the sense that you have on the one hand the monomials, and then on the other hand you have the derivative and powers of the derivative. And so we are going to look at the ring of differential operators in one variable. So we have the derivatives and then some functions, and just the space of these, the ring that these objects build, and I will explain in a second what that means. And then once we have discussed that, I will say a quick word on the Lie algebra, that is the Heisenberg Lie algebra. And this automatically also, relates then to quantization, quantum mechanics. Having a physics background, that's also of interest. But even if you're not interested in quantum mechanics, if you just want to do this symbolic differentiation, then it's good to know about the Heisenberg group and Lie algebra. Okay. So let's get into that. I will go through this text, and you will get a feel for working just in the algebra of this coordinate and differentiation ring. And so this is the list of articles I just pointed to. In the video we're going to look at monomials. They're defined iteratively like that, and as I already pointed out, so we are going to have derivatives. We have the power rule. Coming from analysis, we can prove it, and we take that as a kind of starting point. We're going to use power rule as well as the linearity. And so, for example, if we have here this polynomial where a and b are some elements of the field, let's say they are natural numbers or real numbers. My examples will be natural numbers, although usually you consider fields, or you have the real numbers or complex numbers. But in any case, so let's say you have this polynomial. Taking the derivative, of course, you just get down the exponent, multiply with whatever number is there. You reduce the degree, and this thing is linear, so taking the derivative of a sum is really the sum of taking the derivatives of the individual parts. So here's the first part, here's the second part, works exactly like that. So this is one way of approaching it, and this is how we implemented in the last video the derivative of the polynomial, where we implemented the polynomial just as a list of its coefficients. In this video we do something different, so we still have the linearity and so on, but instead of just applying the power rule, instead of just taking the exponent down like we have it here, where the exponent comes down and this monomials are moved from one to the next, so from x to the power of n to x to the power of n minus 1. We do it bit by bit, and do all computations just in terms of a simpler rule. And so you will see the rule in a second. This is going to be a commutator rule. This is how you define, for example, Lie algebras, and this will be going to get into a particular Lie algebra that you can consider a representation of the Heisenberg Lie algebra. And for that sake, we define all the ingredients that we have here first as operators. Okay, so if f of x is any either you can consider it a function or just a polynomial or infinite series in a ring, it's just an expression of this one coordinate x. Then we define an extra operator for the left multiplication by this x, right? So we say x at applied to, you know, this add is basically applied to the function, is just multiplying this function from the left with x. In that case, if you're just dealing with one dimension, then all the coordinates, which is just x in this case, is commute with each other. Well, it's one dimensional, everything commutes with itself. So in that case, left or right doesn't matter. But in general, if we would deal with a higher dimensional space, then that would matter more. That's why I'm making it more explicit to see how it generalizes. But in this video, we have just x. Then we define a trivial operator. That is just the identity. I call it E here. That if you apply the identity to some object, then it's just the object itself. And then we have the simplest form of this differential operator. So if we apply D to F, then you can read that as just we want to take the derivative of this object, right? And so what we want to do here is we want to actually abstract away this function. We want to abstract away this f of x. Okay, I give the examples of how these operators like act. You know, if I apply x to this polynomial 3 plus x to the power of 2, then we get 3x plus, that works, 3x plus x to the power of 3, right? So for both terms and x is added. If you apply the identity, well, then it just leaves unchanged. If you take the derivative, then by just the power rule that we know, we can take the this rule, and then we get to that expression 2x. This is constant, the derivative is 0. The derivative of x squared is just 2x. So this is how we interpret it if we actually apply it to a function. Now we want to abstract away from actually applying it to anything. But nevertheless, we want to see, okay, how do actually these three operations relate to each other? Or rather, we actually want to know how the x operation and the d operation relate to each other. The identity operation will just be a necessity for convenience. So the thing is this. We have these two objects, d and x. And what we want to get at now is how does the order matter of these operations, right? I introduced this add operation, this email add, really just so that we can actually keep track of the order, that that we don't get confused whether or not we bracket left or right. This is the only reason why I actually introduced this add, so that we don't forget these are like operators. And so when I write d add x add of f, then the point is that to remember that we are always going to apply the rightmost operator first, right? So what happens when if you compute this thing? Well, by the product rule, right? By this rule, where we have this object being x times f, what we get is that we take the derivative of this x. So the derivative of x by the just power rule vanishes. So this is just f plus and then x times and then the derivative applied to f. So this here, given those definitions, is literally just maybe to have an explicit example here on the Wikipedia page. This is basically this here, right? So we have two objects. The derivative of these two objects is the one of them leaving left unchanged, and the derivative applied to one of those, and then the other way around. And the derivative of just x is just 1. So I could also write 1 times f here, and the derivative of x, we don't know what f is, so this is just that, and x is unchanged. So this is clear, right? This is just a product rule. And so let's rewrite this thing again in terms of operators. Then we have just f plus, and then now I write it again down in terms of operators, right? And so we abstract the d out here, and then an x out, and so this is this. So this side is this thing, and now let's subtract this on both sides. So we get that x applied to f followed by d applied to x applied to f minus and the operator switched is just this rule, right? We just derived it from the product rule. And so if we now abstract away this function at all, then this just says that this difference between these operators with and the subtraction with the same operators but switched around is just the identity function identity operator applied to f again, right? So this rule is really just that rule if you just leave out this f. So you could add it back. You can say this is this, right? And now you see why I introduced this identity operator, just so that I have an object that I can actually write on the right-hand side as soon as I abstract it away. So now we have that one rule that tells us how the order matters of this x operator, the multiplication operator with x from the left, and the differential operator. Okay, we can now add this on the other side again, and this line is rewritten just this. So we say d operator x operator is the same thing as x operator d operator plus and then the identity operator. So this is the rule how to like just switch around the operators, right? And so in algebra you write this with this round brackets. This is the commutator. So these brackets just mean consider both orders and subtract them from each other. So for example, you see that the Lie algebra definition has this bracket operation. This is exactly that. So in the Lie algebra, you abstractly say what is this bracket operation, what should come out if you have two elements, and then a rule that mirrors basically some things similar to the product rule. Okay, but nevertheless, we'll not use the Lie bracket anyway. We'll just deal in terms of operators. So now we have the rule how to switch these things around. And so finally on this page, we are already mostly done. I'm now going to work in on basically the example that we had before, where we took the derivative of 3 plus x to the power of 2, and just said, we use linearity and use the power rule, and then we get the result. Now we are not going to use the power rule. We're going to use linearity and the commutator rule, like how to switch the operators around, and we're going to use that applied to a function. The function will be just a constant one function. And the nice thing about it is I will not use any properties of the function that I apply to. I will just use the operator commutator relation, the switch around operation. So okay, what I'm interested in is this kind of expression here. So I constructed it in a way that it mirrors this example. So the example was taking the derivative of 3 plus x squared. And now I encode it with these operators. I have the derivative operator, the d operator, followed by this kind of operator. This is an operator composed of other operators, like a polynomial in various variables. So this kind of operation is multiply by 3, apply the identity, and also apply the x operation on both sides. So for example, like if I were to evaluate this thing here, so this is just a constant function that is always 1. So that would be 3 plus x to the power of 2, right? Because 3, like the identity on 1 is just 1, then 3 times 1 is just 3, and then also plus, I can do this a little bit slower. I can write this as like so. Then I have 3 times 1 plus x times 1, and this is just 3 plus x squared. So this is the meaning of that thing, right? And so here I have this polynomial that we had before, but as operator. It acts on some other function, and that other function happens to be the one here. Okay, and now that we already established the rules how to switch operators around in this operator space, right? This even works with, if you don't consider them operators acting on some function, but just as things in themselves, we can use the rules. Okay, so what we want to do is we want to rewrite it in a way that plays with the order a little bit. So I take this expression, I want to expand it, and then play around with the orders according to the rules we had. But I want to have, in the end result, the x operator always left of the identity operator, and the identity operator always left of the d operator. So this is just an arbitrary choice. I want to represent the whole thing with this order. So what do we do? Okay, we take this operation, this expression. First, we expand it. So I take the d inside. Right? This everything is behaves like polynomials here. It's linear. So the d comes here, the d comes here. Then I expand it also on the right hand side. I resolve these brackets. So I have the sum of these two expressions. And now this is just 3 times identity times d applied to 1. And this will be left alone because this is already according to these rules, right? So there's no x here, but the e is on the left hand side of d. So this is okay. This will not change anymore. But here I have dxx, and I want x on the left of e and e on the left of d. So this d must be pushed through these x's. So I look at this thing here, and now I can use this commutator rule that we have established here. I can switch it around by adding a 1 here. So that's what I do. This is, I can consider this in brackets. I do this one step, I switch them around, and e pops up here. Then I expand again. So I suddenly, from this one term, I suddenly have 2 terms, right? Because the commutator rule gets from 1 term to 2 terms. And here's the same situation again. So there's again something like that. I use the rule again. Suddenly I have 3 terms. Then I expand. I put this x inside. I'm just using normal polynomial rules here, and then expand again, and I end up with this thing. And now I arbitrarily factor this thing out again. I rewrite this again. What I do is I have now these d operators on these sides. So let's actually rewrite this again. And so we see that this expression is equal to this expression given this rule, right? We just use this rule and linearity basically. Okay, and now we have this expression, and now we can drop the standalone interpretation of the operators. Now we say again, oh, actually this d operator, we want to interpret it as a derivative operator. Here is now the first time we actually use the hands-on rule, the action of it, not on other operators, not the relation to other operators, but actually how we act on functions, let's say. And since we have we let that act on 1, then the derivative of 1, the derivative of a constant will be 0, so this will die out. And here we collected 2 times this thing, so we have here 2 times x operator, identity operator. Well, the identity operator on 1 is just 1, and 1 is basically 1x is just x. So we find just by application of these rules of this simple switch around rule, we actually get from 3 plus x squared to 2x. So this is the whole result that we were after. The whole thing here is that we just operated in this space of operators, right? We didn't think so much of like the interpretation as derivative, and it had certainly nothing to do with a limit. We were just using this rule, this abstract algebra rule, and this is what you do with Lie algebras, right? A Lie algebra is some linear space, a vector space, like the polynomial space is a vector space, and you impose some rule, like you can impose some rule how switching two of these elements or vectors around will result in a linear combination of other vectors. You reduce you can change the order, and then you get some other linear terms, just like in this example. And that's what Lie algebras are about, and so you work with just operators. Okay, and so I hope this is clear that there is something like an operator space where you can do calculations just with the operators. And if we now go back to this page on the Weyl algebra, then maybe this definition makes more sense. So in abstract algebra, the Weyl algebra is the ring. So like the polynomial ring, it has this multiplication rules like polynomials, or also integers have multiplication rules. Of differential operators with polynomial coefficients. So you have on the one hand polynomials, on the other hand differential operators. These are the two objects. You can take powers of them like in any polynomial ring, and so that's why these objects are here, finite powers of the d's, and polynomials are also sums of finite powers of the x's. And this would be an expression that is already ordered, right? All these are on the right hand side, on all x's on the left hand side. And the rule really that underlies it is this rule that we already had here. So this expression is 0, right? Here in this case, the y's are like the d operators, the x are like the coordinate monomials, the coordinate operator. And the difference of the order is equal to 1, or you can, if you deal with in the language of ideals, you say the difference minus 1 is 0, and that makes for the Weyl algebra. And you can of course introduce more dimensions. You can say, oh, I look at, I don't know, not just x but x, y, z, and maybe more. Okay, this is basically the first glimpse. It goes in various directions. What can be said is that if you look at some vector space spanned from some elements, and you consider what's called the tensor algebra, then you get this huge space of all combinations where you cannot reduce anything. So this is the vector space that, like, with, you can say, formal basis vectors, where you have no rules how to switch those things around. And then you say, oh, well, okay, I want to consider some rule, for example, our operator rule. You can think of other rules that are more complicated than just the difference is 1. This is basically the simplest rule, you say, just, or the second simplest rule. The simplest rule would be if you just consider polynomials where x times y is y times x. And if you consider something a little bit more complicated that we did here, x times y is y times x plus the identity, then you get the algebra of differential operators. And you can think of other rules. You can say x times y minus y times x equals some combination of linear combination of x and y, and then you have some rule that then makes for if it's linear, then you have a rule that makes for a Lie algebra. And this is then, okay, I will not get into it much more. And then what the enveloping algebra is all about, like the universal enveloping algebra is that if you impose some rule, if you say I want to work with this rule now, then there might be many objects which will fulfill the rule. For example, in our example now, we had coordinate multiplication and differential operation, like taking the derivative as a representation of this rule. But there might be many representations of just this rule, other objects which fulfill the same rule, which we will see in a second. And then if you consider this generic tensor space, then you can say, okay, I want to not just work with this generic space, but I want to work with this space that fulfills the rule, but I will not give an explicit representation yet. And then if you do that, then you're in this universal enveloping algebra. Okay, I hope that was not too out there. So as the last thing, let's consider another the ingredient that's more interesting and more finite. So again, we have dealt with this particular algebra, the Weyl algebra, that has this particularly simple rule of how to commute the operators. And so there are many so-called representations of this rule, many objects that fulfill the rule naturally in terms of their own multiplication plus to between two objects. So what we had now is like basically operators, which means a successive application of multiplication by x or taking the derivative. But for example, this rule is what is known as the Lie algebra of the Heisenberg group or Heisenberg Lie algebra. So this is an algebra of matrices. The simple representation here is just taking three matrices, which are defined like that, 3 by 3 matrices. Only one component is not zero. And then if you take these matrices and multiply them with each other, so for example, if you compute x times y and then subtract y minus x, then it turns out that x times y plus minus y times x, so okay, let me do that here, xy minus yx, then this is exactly the third object. So in that sense, you see that this algebraic correspondence between x, y, and z here to what we had before in terms of d, x, and e, right? This is the same rules. So whether you do use these three objects or the object that we had, these three operators, they give the same rules, and so a lot of the calculations are the same. This is basically the whole game of representations. And so you have, for example, higher dimensional representation. So if you instead of these simple 3 by 3 matrices, you can extend it. So for example, for any finite dimension, really, you say, well, I want to look at the algebra here. So you have some, let's say, 20-dimensional 20 by 20 matrix, and here is some like these are the matrices that have like rows and columns size of 20, and then one element somewhere is just 1. So for example, the first one, the P1 would be 0, 1, and then 18 zeros, and the P2 would be 0, 0, 1, and then 17 zeros, and so on. They're like now I have 20 different of these P's, which are going to correspond to our D's, and then in a similar fashion, but in the last column, you have sorry, I said 20, but it's 18, right? The first element is always 0. So you have 18 QJs. So you have 2 times 18 matrices already, and then you have this final matrix set, which is basically our unity operator. And these matrices also fulfill exactly these rules. And so doing algebraic operations in this with this abstract matrices, like just using the abstract rules, you do the same kind of calculations. And okay, maybe it got a little bit fuzzy here in the last 3 minutes, but the point then of for example, a quantization, like Weyl quantization or geometric quantization, going from some nice, differential geometric real manifold to the quantum world, to this more operator math is just finding ways of passing between these sorts of algebras. Like you go from a commuting algebra in the differential geometric world to the quantum mechanical world. Okay, this got a little bit out of hand. But in any case, I hope you can see that there's this kind of world of just algebraic spaces that are solely defined by some simple rules. The tensor algebra would be the one that its usually has no rules, and then you can introduce rules. They're sometimes introduced here, as we saw, as ideals. So the ideal is another name in this context for what do you want to have as a zero. Yeah, in this case, this is a zero. So this, just to make that clear, that what would be if we take our rule that we had here and just rewrite it as like so. Demand that this is zero, right? It's the same. This equation is the same thing, but now we can say, well, this is our ideal. It's an element of our ideal, at least in our ideal. So this is the thing that generates our ideal, and so you can take these huge vector spaces, choose some ideals, and then make the vector space smaller in a sense that suddenly you can identify and switch around coordinates. Okay, and just as a final note, the Poincaré-Birkhoff-Witt theorem is now a theorem about this enveloping algebras. So this is about these huge algebras that have no more information than just I want to apply this certain rule independent of the representation. And this says something about what you obtain if you switch around basis vectors, and basically it says that once you choose an order, like we said, we want to have what did we say? We have x on the left, and then the d's, and then the e's. This was a fixed order, and you can obviously, in this finite case, like they're just three operators, you can always order them with the rules, and this Poincaré-Birkhoff-Witt theorem is a rule along this line. So it says no matter your procedure of switching around the operators or the basis vectors, basically according to the rules, you get to the same thing. So this is like a uniqueness theorem, and it basically behaves like as if you have, like, once you are at this order that you wish, then these things are basically in correspondence to an algebra where you have no coordinate rules at all, basically. Okay, let's not go there now. But okay, I hope this was an interesting invitation, and you see kind of the point that there's a lot to gain if you look at these big spaces and different representations. One of the things why it's relevant, for example, in computer vision, is that if you want to implement rotations in 3D space, for example, then by isomorphisms between representations, right, between objects that behave the same, even if they're different, definitional different, then but you get the same kind of information out of them by manipulating them. Then once you have these isomorphisms, then you can choose your representations. Where they are the same, you might find that the calculation rules are simpler for ones or the others. And so, for example, in computer vision and robotics and so on, Lie algebras relate to rotations in 3D space, and quaternions would be representations of rotations that on the bulk of the manifold give you the exact same result. And so there's a use for that. And this not just goes for rotations, but also for basically any nice group theoretical, let's say, movement through your spaces. Okay. I hope that was of interest, and see you for the next video where I will actually step through this nice paper. Take care.